Hello guys, welcome to Mathematical Bridge channel. So in this video you are going to learn the basics of number theory, which includes factors, multiples, Hcf and Lcm, and congruence modulo. So let's start. So factors and multiples means so for example we have 6 and we know that 6 is a multiple of 2. So in factors and multiple terms we can So in factors and multiple terms, 2 is a factor of 6. 2 will be a factor of 6 and 6 will be a multiple of 2. So this is the basic definition. And now for a particular number of particular and so if a number is x raised to a into y raised to b into z raised to c. So if we have a number and this is true for every number, so we can represent every number uh, in the primes. So basically the primes are the atoms of our number system. So we have, let's say, 6. So 6 is equal to 2 raised to 1 into 3 raised to 1. And let's say another example, 85 is equal to 5 into 17, 5 raised to 1 into 17 raised to 1. So for each number greater than 1, we can represent it in the form of prime numbers. And 1 is the only exception because we cannot represent 1 as prime numbers. So what this number of factors is a plus 1, b plus 1, c plus 1. So what this means is basically that uh, so for 6 we have factors are 1, 2, 3, 6. So there are 4 factors. So what this theorem or whatever is telling us that it is telling a way to calculate these number of factors in a very fast way. What we used to do in our school, we used to draw a column and we used to do this 1 into 6, and then we used to do 2 into 3, and we used to and then count the factors. So what this method is very important because it gives us a very short trick, or it's very logical trick, so to calculate the number of factors very fast. So the proof of it is very simple. So we have a number c is equal to x raised to a into y raised to b into y raised to b into z raised to c, and so on. There are, if there are x1 raised to a1, x2 raised to a2, dot dot. So there are n prime numbers in the factorization of a number. So xn raised to an. So now this theorem is telling us, so we have to prove that the number of factors of this number is this power plus 1 into a2 plus 1. So a1 plus 1. So we have to prove a1 plus 1 into a2 plus 1 into an plus 1. So now, so first let's observe. So the factors we can see are x is there, x raised to 2 is also a factor, dot 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 till x raised to a1, whatever is a1. Similarly, we have y as a factor, y square as a factor, dot 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 y raised to sorry x2 dot 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 x2 raised to a2. So there are a1 factors here, a2, and similarly there will be a1 plus a2 dot dot plus a and such factors. Now x1 x2, and so this is the basic idea. So what we are doing is basically this: x1 plus x1 square, x1 raised to a1 into, so similarly x2 raised to a2. So now if you'll notice that we'll take one, wait a minute, xn raised to an. Now if you'll notice this, that x1, if you take, so what you basically do to expand this expression, you basically take one variable from this bracket and multiply with others. So what you will notice that x1 into x2, oh, here it should be 1 also. So what you will notice that if you will take x1 from this bracket and multiply it with 1 1 1 all ones, then you will have your factor to be x1. And if you will take x1 square and multiply all the brackets with 1 1 1, so we'll have x1 square as its factor. So basically what you're doing is you are taking one term, any one term from these a1 plus 1 terms, and multiplying with the other terms. So you are choosing a1 plus 1 terms from this bracket, a2 plus 1 terms from this bracket, and dot 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 you are choosing. So the number of factors would come out to be a1 plus 1 into an plus 1. And thus we have proved it. And similarly, there is also another way to prove this. So what you're basically doing is, so this is a combinatorial way to prove this. Another way. So x1 raised to a1 xn raised to an. So the number, so divisor is basically the sum n is equal to x1 raised to, so it will be something like this. Divisor would be l dot 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 xn raised to l1 dot 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 something xn raised to ln. And here l1 ln can also be 0, because if it does not have xn as its prime factor, the divisor, so n is a divisor of c, so it cannot have x1 as its divisor. So l1 ln can all be equal to 0, or some may be 0 and some others may not. So what this means is that l1 can be 1, so l1 can be 0, 1, 2 dot 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 a 1. Similarly l2 can be 0, 1, 2 a2. So and this would go on, go on, go on. So ln is equal to 0, 1, 2 dot 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 an. So you can choose any one of these exponents. So there are a1 ways to choose it. We will choose 0 1, so there are a1. Similarly, there are a2 ways, oh sorry, a1 plus 1 ways to choose it. So there are a1 plus 1 exponents possible. Here we have a2 plus 1, so a2 plus 1 ways to choose the exponent. Similarly, we have an plus 1. So the number of divisors would be equal to, we'll have it to be a1 plus 1, an plus 1. Thus, we have proved it. Now moving on to HCF and LCM. So we all know HCF and LCM, it's the basic thing. So there are some symbols which you need to be familiar with. So GCD of A comma B. So this basically means the HCF. GCD is the another name of HCF. And you all know GCD of A B. So two numbers is equal to LCM of A. B is equal to A into B. So, but we do not know the proof of this. So, we'll now prove this GCD into LCM is equal to product of two numbers. So, what we'll do is for example, we have 9 and 18. So, GCD of 9 and 18 is 9. So, what we are going to do is that we are going to assume GCD of A and B to be K. So this means that K divides both A and B. K divides A. K divides B. So this means that A is K into something. So let it be Q. And similarly B is K into something. Let it be T. Now we also know that GCD means that it is the greatest common divisor. So let's say that Q and T have a common factor. We'll assume, let's say that Q and T have a common factor. So what this means is that there is a number 2, 3 which divides both Q and T. So if there exists a GCD K and T and Q, let's say it be L. So then it would mean that A is K into L into something, something. So B would be K into L into something. So this would mean that KL is GCD of A and B. This would mean that the GCD would change. We can clearly see this because scale divides both A and B. So this means that our assumption that K is our GCD is getting wrong. So this means that our assumption that GCD of T and Q is not is something which is not equal to 1 is not possible. Therefore, GCD of T and Q is 1 and therefore they are coprime. So if they are coprime, then our LCM would be KQT. And why it would be? Because LCM is basically the multiple. So let's say our LCM is KQ into alpha equal to KT into beta. So now these both are equal. So Q alpha is equal to T beta. Now we know that Q and T are coprime. So alpha upon beta is equal to T upon Q. Now we know that T and Q are coprime. GCD of T or Q is equal to 1. So this basically means that T and Q are in its lowest form. So this means that alpha and beta, so if we need to, so we know that LCM is the least common multiple. So this means that we have to minimize alpha and beta both. So for this to happen, alpha has to be T and beta has to be Q. And so our LCM would be KQT. So now if you'll check LCM, so if you'll now check LCM into HCF would be equal to KQT into K. So our assumption was K is GCD. So which is equal to, so if we'll say this, that it is basically KQ into KT, and KQ and KT were our numbers which are assumed by us, which are A and B, and thus LCM into HCF is equal to A into B. So now let's move on. So C, now this is a very basic. So GCD of A comma B is GCD of A comma B minus A. This part is a little bit difficult to understand. So what does this mean is, so if GCD of A comma B is, let's say it would be D. So D divides A and D also divides B. So if you'll subtract both, because if you'll subtract both, then that the outcome will also be divisible by D. So D also divides B minus A. Thus, as D divides A and D divides B minus A, therefore GCD of A comma B minus A would be equal to D. So now we have GCD of A comma B minus A equal to D. And now some of you will ask that we have just proved that D divides B minus and D divides A, and it does not mean that GCD of A and B minus A is D. But let's say that there exists a GCD, so we'll do this by contradiction. So let's say there exists a GCD, so that multiple which divides both greater than D. So if it exists that it divides both, if there are multiple exists greater than D, let's say it will be L. So L divides A, L divides B minus A. So basically it would mean that L divides B. So it would mean that GCD of A and B would be equal to L, and thus it would be a contradiction to our assumption that GCD is D. Thus GCD of A comma B is GCD of A B minus A, and thus we can use this property in our sums. And now this very simple property, GCD of A and A plus 1 is equal to 1. So it is very obvious because we have already proved GCD of A and B is GCD of A minus B, A B minus A. GCD of A plus 1 is equal to GCD of A and 1. Now GCD of A of 1. So a number, greatest number dividing both the numbers A and 1 would be 1. Simple. This we have already shown. Now we'll move on to the congruence modulo part. So it is not, so seeing that sign here you would get feared, but it is very simple. So what this sign basically means is that if y is congruent to z mod x, so this sign is basically telling us that x divides y minus z. So for example, 7 is congruent to 2 mod phi because phi divides 7 minus 2. Thus, and here are some properties like if x is congruent to y mod n, then x raised to p is congruent to y raised to p mod n for p belonging to n. So this is very simple. So if x is congruent to y mod n, x is congruent to y mod n, then we will have n divides x minus y. Now if you'll notice that x raised to p minus y raised to p, if we can easily factorize this to be x minus y into x raised to p minus 1 plus y raised to minus y into x raised to p plus p minus 1, and this would be, and this process will go on up till y raised to p minus 1. Thus this means that x minus 1 is a factor of x raised to p minus y raised to p, and thus x minus y divides x raised to p minus y raised to p. And we also know that n divides x minus y. So if n is a factor of x minus y and x minus y is a factor of x raised to p minus y raised to p, then n also is a factor of x raised to p minus y raised to p, and thus n divides x raised to p minus y raised to p. And thus using congruent modulo signs, we can write it to be x raised to p is congruent to y raised to p mod n. Now there are some properties. If a is congruent to b mod n, so if a is congruent to b mod n, then we will have c is congruent to d mod n. So if a is congruent to b mod n and c is congruent to d mod n, then a plus c is congruent to b plus d mod n. So how will we prove this? Is basically simple. N divides a minus b and n divides c minus d. So the sum of those numbers would also be the multiple of n. So n divides a plus c bracket minus b plus d. So you can write a plus c is congruent to b plus d mod n. And no need to remember these properties. It's, you can easily derive these. Now, if and if A is congruent to B mod n and C is congruent to D mod n, then AC is congruent to BD mod n. So as n divides A minus B and n divides C minus D, n divides A minus B into C minus D, because the multiple will also be divisible by n, because they both are divisible by n. So n divides AC minus BD AC minus AD AC minus AC plus BD. Oh, I have easier way to do this. So if n divides AC, if n divides A minus B, then the multiple will also be resolved by this. So n divides AC minus BC. So and similarly, if n divides C minus D, then n divides BC minus BD, and thus its addition will also be divisible by n. Here we have n divides AC minus BC, n divides BC minus BD. So that addition will also be divisible by n. So n divides AC minus BD, and now we can write it in congruence form. So AC is congruent to BD mod n, and this is an important property, which is AK is congruent to BA mod n, mod n divided by GCD of K and n. So if K is congruent to BK mod n, then A is congruent to B mod n divided by GCD of n comma K. So what we are given is that AK is congruent to BK mod n, and we have to prove this. A is congruent to B mod n divided by GCD of n and K. So this means that n divides K into A minus B, and we have to prove this A is congruent to B mod n divided by GCD of n and K. So let's say GCD of n and K is D. So D divides both n and K. So let n be dt, not your integration dt. So and K is dy. So dt divides dy into A minus B, and thus if dt divides dy into a minus b, then t divides y into a minus b, and t, if you will notice that gcd of nk is d, so n by d is t, and thus t is n by gcd of nk. Thus we have, and we also know that t and y are co-prime because gcd of n in k is d. So t and y are co-prime. So if they're co-prime, so t cannot divide y. So it has to divide a minus b. So this means that t cannot divide y. So t has to divide a minus b. So a is congruent to b mod t. A is congruent to b mod t. Now you'll notice that t is basically n divided by gcd of nk. So thus we have proved this property. And now you'll notice that we have done so many things like this and prove these properties in congruence modulo. But why we need this symbols and systems to do this? We can directly write A is divides C minus B and this. So this congruence modulo is has a very good application in number theory, which is used to solve Diophantine equations, and you get unit digits and remainders, and it is vastly used, and it has uh, so to find unit digit of a given exponential is a common question that we find in some exams, this type of easily. So find remainders and easier our work, and it helps in dealing with equations. So congruence modulo. So for example, we have find last two digits of some positive integers. Is we have to prove that last two digits of 76 raised to n is always 76. So basically we'll prove this. So if you'll notice that n, if a number can be represented as 10 raised to x, a raised to x, dot plus a naught, and where these are basically digits x, ax minus 1, dot a naught are basically digits of number. Okay, so if you'll notice that we'll have 10a1 here also, 10a1, 10a1 we will have here. And now if you'll work in mod 100, you will see that others here are divisible by 100, and thus you will have the last two digits of the number, or the basically the last two face value of the last two digits we will get if you'll work in mod 100. So if you'll divide your number by 100, then you will get remainder as the last two digits place value, sorry. So if n would be congruent to its last digits, a1 a naught, last two digits place value, mod 100. So what we need to prove is that 76 raised to n is always 76 last digits. So if basically we can prove, so if we can prove that 76 raised to n is congruent to 76 mod 100, then we are done. So what we need to basically prove is that 100 divides 76 raised to n minus 76. So and 76 is 4 into 19. So this means that 4 divides 76 raised to n minus 76. So we need not, and we and so if you will see the factorization of 100, it is 4 into 25. So if we somehow prove 25 divides 76 raised to n minus 76, then we are done. So if we prove 25 divides 76 raised to n minus 76, then we will be done. So if we prove 25 divides, we know that 76 is not divisible, so there's no use proving it. So we can take 76 out. We'll take it in brackets and cancel it off. So it's 20. So if we somehow prove 25 divides 76 raised to n minus 1 minus 1, then we will be done. What you'll notice is that 76 is congruent to 1 mod 25, because it is 25 into 3 plus 1. And now we had learned in the theorem that its power is also divisible. We can raise it. We'll use that property here. So 76 raised to n is congruent to 1 raised to n mod 25, and 1 raised to n is basically 1. So 1 mod 25. So this means that 25 divides 76 raised to n minus so raised to n minus 1 here. So this means that 25 divides 76 raised to n minus 1 minus 1, and thus 25 will also divide its multiple, because if it is dividing this number only, then its multiple would also be divisible by 76 25. So if we multiply 76, then it would make no difference. So 25 divides 76 raised to n minus 76, and we also know that 4 divides 76 raised to n minus 76. So therefore 100 divides 76 raised to n minus 76. And if 100 divides 76 raised to n minus 76, then we are done, because last two digits. And thus you can now feel the essence of why congruence model is important. And because we have proved a very strong statement here that last two digits of 76 raised to n is always 76. Similarly, we have last two digits of 5 raised to n is always 25. So 5 raised to n is congruent to 25 more 100 we have to prove. So we know that 5 raised to n minus 1 is divisible by 4, congruent to 4 divides 5 raised to n minus 1. And 25, so 4 divides 5 raised to n, so n minus 2 minus 1 will also divide, because let's explain from starting. I moved on a very fast. So if phi is congruent to 1, we know that phi is congruent to 1 mod 4. So phi raised to n minus 2 is congruent to 1 raised to n minus 2. So 1 mod 4. Thus 4 divides phi raised to n minus 2 minus 1. So 4 will also divide its multiple. So 5 raised to n minus 25. 4 divides 5 raised to n minus 25. And we know that this is divisible by 25 clearly. So 100 divides 5 raised to n minus 25. Thus last two digits of 5 raised to n is always 25. Now last two digits of 7 raised to n changes periodically in the pattern 0, 7, 49, 43, 01. So we need to prove this basically. So if you'll notice this, you will feel a very different way, and you will not be it is not very intuitive in the starting. So if you'll notice, you will check the powers of 7. So let's check. First is 07, last digits is 7. And 7 square is 49, last digit is 49. 7 cube 343, so last digit is 43. If you'll notice here, 2401, so last digit is 1. So basically you will have 7 raised to 4 is congruent to 1 mod 2401, 1 mod 100, sorry. So we'll use again our property. 7 raised to 4k would be congruent to 1 raised to 4k, and 1 raised to 4k is basically 1. So 1 mod 100. So if 7 raised to 4k is congruent to 1 mod 100, then we'll again use our so 7 raised to 4k plus 1. We'll multiply both sides by 7, because as 100 divides 7 raised to 4k minus 1, then its multiple is also divisible by 100. So 100 divides 7 raised to 4k plus 1 minus 7. 7 raised to 4k plus 1 is congruent to 7 mod 100. Similarly, we will do this. So we will have 7 raised to 4k plus 2 with its mod 100. We will have 49. 7 raised to 4k plus 3, 43. Thus, if you will start the pattern from 1, so 7 raised to 4k plus 1 on division by 100 has 7. So its last two digits is 07. So last two digits of 7 raised to 4k plus 1 is 07. 4k plus 2. So 7 square has 49 as its last two digits. 43 and 01. So what we have done is formally prove the pattern which we were noticing by checking the powers of 7. We are seeing that 7, 49, 343 are coming. We were seeing that it is repeating. So 16807, it is 07. Again we will have. So what we did is that we formalized this loop which was again and again occurring. Similarly, we can. This is also interesting question. You can try it. 36, 16, 19. So try this question and comment down below. So this is the end of the video. Thank you for watching the video. Please join our Telegram channel, hit the like button and share the video. Thank you.